So this particular example, which is the EX14 example in my live lessons Java 8 folder, shows the difference in overhead using a parallel spliterator to split a Java linked list versus an array list. And of course, both of those are lists, and they both have the capability to be split, but you'll see that there's a big difference between their performance. And then we'll also show some of the overhead in differences in overhead between combining and collecting results in a parallel stream versus a sequential stream using concurrent and non-concurrent collectors. So this will be a fun example that kind of delves into some of the collector issues. Here's what we're going to do. We are going to take the complete works of Shakespeare. You may be detecting a theme here. So I've got a file that has all, 37 of his plays and another file containing all of his sonnets. And here's the program. So we're first going to run the spliterator tests. And while I'm doing this, let me go ahead and run these things. They take a while to run, so I'll let them run in the background. So we're first going to run the spliterator tests. Let's see what those do. So here's what the spliterator tests do. They're going to create tests for different sizes of input, starting with the first 1,000 words in Shakespeare, the first 10,000 words in Shakespeare, the first 100,000 words of Shakespeare, and the first million words in Shakespeare. I think there's something on the order of about 800,000 words in Shakespeare. So this will cover the whole gamut. So what we do is we go ahead and we open up the data file containing all the works of Shakespeare, and then we split the input up into words by ignoring white space. So it basically takes the complete works of Shakespeare and then makes individual words for everything, and we limit it to a certain amount. And you can see how we do that here. We load the file containing Shakespeare. We read all the bytes of that into one absolutely gigantic character sequence. We then go ahead and split things, and we split them using the regular expression, which was basically white space. So we now have a stream of words in Shakespeare. We filter out anything that happened to be empty, and then we limit ourselves to the first limit number of strings in Shakespeare, or words in Shakespeare. We collect the results into a list. Notice how clean and cool that is by using the Java 8 features like split as stream and filter and limit and collect and so on. So we take the list of words, and now we do two things. So we got this back as an array list, and now we copy it into a linked list. So we have a linked list representation of Shakespeare and an array list implementation of Shakespeare. And then we go ahead and we time how long it takes to uppercase all the words in Shakespeare in parallel using an array list, and how long it takes to uppercase all the words in Shakespeare in parallel using a linked list. And I will show you what the results are. So if you take a look here, this is the results of running this stuff. And you can see here for, let's see, where is it? You can see when we have just 1,000 words, there's not really a difference between the linked list versus array list implementation. When we have 10,000 words, you can see that array list is holding steady, but linked list is taking longer. When we've got 100,000 words, you can see that array list is about twice as fast as linked list. And then when we've got all the words in Shakespeare, as you can see, there's 883,311 words by my reckoning. Then you can see that array list is just way, way faster than linked list. And that's because splitting an array list is more expensive than splitting a linked list. And this is the actual code. You can see here, we go ahead and create a string, a list of strings, and then we go through a certain number of iterations, which in this case is 10. And we're going to take the words, and then in parallel, we will uppercase them, collect them into a list, and stick them at the end of this list that we've got. So what we're really doing is measuring the overhead of how long does it take to split an array list versus a linked list into parallel chunks and then run them in parallel. So just kind of fun example there showing you why you want to go with array list rather than linked list most of the time. Let's now go ahead and take a look at the joining tests. So this will demonstrate the differences in performance between concurrent and non-concurrent techniques for joining results into a stream. Once again, we have different numbers of words in Shakespeare. We get words from the file, and then we are going to time the amount of time spent to join things together via collect and collectors joining, and we'll take a look at that, in a sequential stream versus a parallel stream. So let's go ahead and take a look at this. In this case, we're using the array version of these things. So here is time stream joining. And you can see how what we're doing here is we are collecting the things together. So we're going to basically create a stream of words and then conditionally turn that into a parallel stream or not, which is a really cool technique that you should know about. So you can dynamically turn a stream to be parallel or not based on a parameter that you pass in here. So if you pass in parallel, then it will go ahead and turn the stream to a parallel stream. Then in a real world application, you do something interesting at this point. But what we're going to do is we're going to collect everything together and join them all back together again. So let's go ahead and see what happened when we ran those test programs. So here's the joining. So for 1,000 words, sequential versus parallel, they joined in about the same amount of time. For 10,000 words, you can see that doing the joining sequentially was faster than doing the joining in parallel. For 100,000 words, you can see that the parallel version, sorry, I got that wrong. Yeah, no, that's right. For 10,000 words, it was actually faster to join things sequentially. But when we get 100,000 words, parallel joining is winning. And when we get all the words in Shakespeare, parallel joining is definitely winning by a factor of 2. And what this is really illustrating is that n times q model I've talked about before, where n is the number of elements and q is the amount of time doing work. And as n gets bigger, you expect to see bigger improvements from using parallel performance. When you're not using a large number of elements, the overhead of parallelism may swamp the benefits of parallelism. And then the last thing we're going to look at here, I think, is the collector tests. And this is kind of fun because it shows the difference between concurrent and non-concurrent collectors. So again, we have a bunch of different sizes of data, words in Shakespeare. And this time we're going to have basically 4 different variants to test. So we're going to use collect to set, and this is the non-concurrent version. And we do this both with basically parallel streams and sequential streams. And then we're going to use a concurrent collector and do that for sequential streams and parallel streams. So if we go and look at this stuff, let's first look at the non-concurrent version. This is just classic collect things into a hash set. Hash set's just a hash map that's a set with just keys. So we just use just a good old non-concurrent collector, nothing fancy, nothing extravagant there. But if we take a look at the concurrent version of this, you can see that we use a concurrent hash set collector. And this is going to be set up to use a concurrent hash map as opposed to a non-concurrent hash map. So it's going to use the concurrent version. And if we run these different tests, what you'll see is pretty interesting. So here's the collector result. For 1,000 words, it doesn't really matter. For small n, whether it's doing it in parallel, whether it's doing it sequentially, whether it's doing it with a non-concurrent collector, whether it's doing it with a concurrent collector, doesn't matter. For 10,000 words, you can see that actually sequential is doing better. Sequential is winning for that size because it doesn't have much to do. It's very fast. And moreover, you can also see that the parallel version is also working better than the parallel streams is working better for non-concurrent collectors when n is relatively small. However, when we get to 100,000 words, you can see now that the parallel streams are winning, and we're also seeing that the concurrent collector is winning. And then when we get to all the words in Shakespeare, again, you can see now that the parallel stuff is winning, and the parallel streams is winning with the concurrent collector. So the bottom line there is when n gets big, you get a bigger bang for your use of parallel streams, number one, and concurrent collectors. Whereas when you have small n, it's not as big of a deal. So this is actually what you'd expect. You would expect that as n gets bigger or q gets bigger, whenever n times q gets bigger, you're going to get a bigger bang for your buck by using concurrent collectors, especially for collections or mutable result containers that are expensive to merge together. And you can also see, of course, that doing this in parallel as n gets big is better than doing it sequentially. Okay, so that's the end of that discussion. I think hopefully at this point you've got a pretty good feeling for the different variations that can be used in terms of splitterators that are going to be working for parallel streams or not, and whether or not they're efficient when used in parallel, like ArrayList versus LinkedList. So that's one piece of the puzzle. We looked at joining, how you join things together, how those differ based on parallel processing. And then we looked at using the collector and concurrent collector versus non-concurrent collector for both sequential and parallel streams.